on black holes and thermodynamics.
Great. Thank you, Clifford. Okay, so today's lecture is going to be about the thermodynamics of black holes. And we're going to use a tool called Euclidean field theory that I will be explaining along the way. This follows on in a natural way from where I stopped last time because I will use the technology from the first two lectures. But I should mention that this lecture is at a slightly more advanced level than the first two. So just be aware of that. And furthermore, on Friday, I guess I've been scheduled for an extra discussion, maybe some partial lecture. Very likely that will be again at a even slightly more advanced level. You should just be aware of that. Nevertheless, feel free to ask questions and slow me down if it looks like I'm moving too quickly. All right. Second of all, people have been asking me for references, which is always a good idea. I have 5 here to suggest for you, which covers both the material that I've already talked about, as well as the material I will talk about today, and some other perspectives I won't get to. In particular, several people have asked me where to find a treatment of black holes like what I gave in the first 2 lectures. I know only one place to find it, and that is here. These are lecture notes from a course that I taught at Syracuse University some years ago. So this is physics.syr for Syracuse.edu, courses PHY 312.03 spring. And the note here is that I have forgotten whether it's a capital S or a lowercase s. I'll let you sort that out yourself. Okay. But I'll just warn you, this is about 300 pages of lecture notes on special and general relativity at a somewhat lower level than we've done so far. But you may find it interesting. But nevertheless, the treatment I've given on black holes is a combination of chapters 5 and 9 from this set of lecture notes. Also, for the material today, these 2 references are relevant. It turns out that much of what I'll say today is in Professor Z's quantum field theory book, which has already been well advertised. There is a section about black holes, and it follows a treatment much like what I'm going to do today. For a different perspective and some additional information, I strongly recommend these lecture notes from another school by Ted Jacobson. And here is the GRQC number you can download. This will introduce students who are interested in the subject of quantum field theory and curved spacetime and talk a lot about black hole thermodynamics. And then finally, 2 brand new but very good general relativity textbooks that certainly cover much of this material are the General Relativity text by Sean Carroll, S. Carroll, and one by Jim Hartle, J. Hartle. So I recommend that you write down all of these references and when time permits, have a look at them. Yes?
Just for those who aren't familiar with the archive, perhaps you can put the rest of the GRQC.
Let's see, yes. HTTP. What's the South African one? Right. ZA.archive with an X? And IV.org? Or is that it? That's it? No.
Just get the standard one and it'll
okay.
you to the
www.arxiv.org/ and I believe if you want to just type this in as a web URL, you then type ABS/ and then this. Okay, and that will extract this lovely set of lecture notes off the web and introduce you to the marvelous physics archive in general. Good. All right. Well, let's get started here. As I said, this is at a slightly more advanced level, but I want to find out what the students know. I'm going to be talking about thermodynamics. And let's just take a beginning step. How many of you are familiar with the fact that thermodynamics, of course, involves fluctuations, and you assign probabilities for certain things to happen? And the most important thing about thermodynamics are the set of Boltzmann weights, which tell us the probability for something to happen due to a thermal fluctuation, probability, is proportional to e to the minus the energy divided by Boltzmann constant times the temperature. Okay, how many of you are familiar with this statement? About half of you? Okay, most of you. Good. Most of you. Good. All right. I will have to sort of assume this. This is a basic property of thermal physics. I'll say just 2 words about it for those of you who don't know this. The idea is that in thermal physics that one doesn't worry about following the dynamics in detail. One simply looks at the aggregate properties of systems. And it turns out, it was shown by Boltzmann over 100 years ago, that generically, if one assumes nothing else about what's going on, this is the most likely distribution of energies is given by this. In other words, if you look at what's happening in a box of gas, and you simply ask what is the most likely configuration for the entire box, the answer is that the energies of the individual atoms or molecules will be given by this expression. That is, there will be less molecules at very high energies, more molecules at lower energies in exactly this relation. Okay. Now, skipping ahead a bit, as a result, the operator in quantum mechanics, which is useful for doing thermodynamics or statistical mechanical calculations, is e to the minus the Hamiltonian divided by, again, k times t. Okay. Actually, I, like Professor Z, believe that k is 1. Therefore, I will not write that down. And for those of you who have not seen this before, I'll mention that it is conventional in this subject to introduce a parameter beta, which is the inverse temperature, so that the interesting operator is indeed e to the minus beta h. And in fact, one of the things that you learn if you study a full course in statistical mechanics is that you can calculate all the thermal properties of a system by looking at not just this operator, by looking at this operator, but in particular, you don't have to know all the details of the operator. All you have to know about the operator is the trace. This is typically called z, or z in this part of the world. It has is the name of the partition function. And from this object, one can calculate everything one needs to know. Good. Now, actually, that's probably enough background to follow my lecture, but let me just find out how many of you have learned about partition functions before and sort of vaguely know what they are. Okay, a reasonable fraction. For those of you who don't, I suppose I should add an extra exercise on here to, again, ask your friends in one of your study sessions, what is a partition function and how do they work? But I'm going to proceed on from here. All right. So this is what we're talking about. We want to calculate this partition function for some system. Actually, what I'm going to do here is, for the moment, I will say nothing about black holes. I will merely introduce what are called Euclidean field theory techniques for thermodynamics. So imagine that we're starting over. You don't need to have learned anything that I've said before. Imagine that I am, in fact, Douglas Smith a week ago, okay? Except that instead of quantum mechanics, I'm talking about thermodynamics. And instead of, Douglas Smith told us a lot about how to calculate this operator, e to the I h t, the time evolution operator of quantum mechanics, right? So imagine that instead of calculating this operator, we wish to calculate this operator. You see, they are, of course, very similar, right? They've both got an e, and they've both got an h, and they've got something else in the exponential. So these two quantities, you see, are in some sense related if we were to set beta equal to I times t. Thermodynamics and time evolution are intrinsically related because they have the same mathematical kind of expression. Okay. So now I will explain to you the relevance of the word Euclidean to thermodynamics. This operator has to do with calculating things that happen in time, right? And we've talked a lot about the Minkowski space. We talked about Minkowski space and about the Minkowski metric. We've talked about the fact that the properties of Minkowski space are encoded in this formula, minus dt squared plus dx squared. So now, what happens if I simply replace, t by minus I beta? Well, clearly what happens if I make that replacement is that I get ds squared is equal to now plus d beta squared plus dx squared. So in some at least mathematical way, we will see that there is a relationship between thermal effects and things that happen in a space-time of Euclidean type. This is a space-time, this is the rule that governs distances on a normal flat plane like the blackboard, because you see this is just the Pythagorean theorem in disguise, right? This says that if I have a triangle, one leg has side x, the other has side beta, that the distance, s, is given by s squared equals beta squared plus x squared. It's the Pythagorean theorem. Okay. So this removes all the funny business about relativity, but makes time an extra direction like space. Okay. So these are motivational comments to show you where we're going. But now let's try to do a calculation, much like what Douglas Smith did here. Actually, I will stop, and I believe I will reiterate much of what he said, but for this operator instead of this operator. Now, I hope this is more or less a review, but I didn't see this lecture of Douglas's, so it may also be new. Okay. Any questions before I go on and actually do the calculation to link e to the minus beta h to a Euclidean space more concretely? No? All right. Yes?
In that relation there, he was temperature or time or something.
That's correct.
So are you doing something like continuation?
What I am doing is an analytic, excellent question. What I am doing is, in fact, an analytic continuation. So although there is a formal relationship between t and beta, which goes like this, I am interested here in the case where t is real, and I'm interested here in the case where beta is real. As you say, those are not simultaneously true. This is very much related to, although not exactly the same thing, as what happens when you study complex analysis and you use Cauchy's theorem to transform an integral along the real axis into an integral along the imaginary axis. As you say, you're doing an analytic continuation, so you're using the mathematical property of analytic functions to relate this line to this line, even though they are certainly not the same line. Same thing is going to be true here. As we know, this function is wonderfully analytic. The exponential is analytic. It's the best example of an analytic function I know of. So this operation will be quite reasonable. Okay, good. All right, well, other questions? No, then let us proceed. All right, what I wish to do, as I say, is to calculate the partition function. This is fundamentally the trace of this operator, e to the minus beta h. Okay, now, how do I calculate the trace? Well, let's suppose that for the moment we're just doing quantum mechanics. So let's assume that the Hamiltonian, I'll write it up here, let's assume the Hamiltonian is some function of a coordinate that I will call q and a momentum that I will call p. Very good. Then how do I calculate the trace? Well, I do it by considering matrix elements of this form, say, q e to the minus beta h, and I'll put the other q over here for reasons that will be clear in a moment. So I compute the expectation value in each coordinate eigenstate, and then I integrate over q. And that happily computes for us the trace. Okay. Now, I want to make this more complicated, though. Oops, should have left myself some more space. Well, we'll fit it in. Much as I believe Douglas Smith would have done, it turns out to be useful to go ahead and stick in by hand what's known as a resolution of the identity, meaning I will also choose to introduce a dummy variable, which is momentum, to integrate over it. And here, I will introduce a complete set of states. Clifford. Yes?
People might be wondering whether that trace is related to the traces that they do in Boolean matrices.
Yes.
It might be just worth showing that there's just like some of the diagonal elements in the matrix.
Very good. It is, in fact, exactly like some of the diagonal elements. I guess the way to, what Clifford would like me to say is that a generic matrix element takes this form with two different entries on the left and right. What we have done here was to consider the case where q and q are the same, That's the diagonal elements of the matrix, just like in a square matrix. If I label these 1, 2, 3, 1, 2, 3, the entries where I choose 1 and 1, 2 and 2, 3 and 3 are indeed the diagonal elements. And this integral here is the same as summing them up. So that performs the trace. Okay. And now, just so I know how fast to go, can someone tell me briefly whether indeed this looks like the path that Douglas Smith followed in his calculation? Good. Okay. Excellent. Like I said, hopefully I will simply repeat what he said, but with no I here and a minus sign instead. All right. So in that case, you've seen before that even though this looks like an odd thing to do, and we've introduced some extra integration variables, in the end it gave a useful expression. So I will do the same thing again. I will, in fact, choose to introduce a large number of other dummy integrals. Right? Recall, this is the story that in quantum mechanics, the unit operator is the integral over dp of p and p, and it's also the integral over dq of q and q. So I'm free to insert this kind of expression as many times as I like. And in fact, I'll insert it many times. I want to consider the case where I add a large number of additional coordinate integrals, 1 through n, and also a large number of additional momentum integrals, 1 through n. Okay? I will do this in a clever way. I will do this in this form. We'll put together a product over the index j with the coordinate qj here, e to the minus beta h over n, pj, pj, and qj minus 1. Now let me just explain this. What we're doing then is I've actually taken this term, e to the minus beta h, broken it up into products of n operators, each the same thing with 1 over n in the exponential. And then for each of those, I've stuck in a complete set of coordinate states and a complete set of momentum states. Here are the two momentum states side by side. So you see that when I do the integral over p, these just become the unit operator and go away. The q's also have that property, but you see to see that, I have qj as the first term in the jth, as the first part of the jth factor. And over here I have qj minus 1. So that means when I shift the index 1, I'll have a qj here as well, and then the last bit of one factor will combine with the first bit of the other factor. When I do the qj integral, it will also turn to an identity matrix and go away. So here, this is just equal to the first thing written out in what looks like a more complicated way. Is that clear? Okay. Oh, I should mention, you might wonder where the original q and p went. I have chosen here to identify Pn with the original P, as well as Qn with the original Q. And you'll notice that because j can be 1, I'll put that in explicitly, j is 1 to n, I also have a Q0, because there's a j minus 1 here. And so it turns out I also need to identify this with Q0, so that indeed I get the same thing on the far left and the far right. So what's interesting to note here already is we see that naturally the set of q's is something that's arranged in a circle, because we want to number these starting with q0, q1, and so on around the circle to qn minus 1, and then qn is again equal to q0. So that's an interesting property that we'll make use of later. All right. So far, we have simply taken what looked like a simple expression and made it look much more complicated. Okay. However, when n becomes large, one can write this in a useful form. And the reason one can write it in a useful form is that when n becomes large, this matrix element, q, e to the minus beta h over n, p, okay, can be approximately written as follows. It can be written approximately as e to the minus beta h of pq, let me explain what this is, times q p. So here what I have done is this h is the quantum mechanical operator. Okay. And here what I have done is simply to take, so it might be, for example, we might have had h is q, let me put a hat on the operators, plus p squared. What I've done here is essentially just to drop the hats and say, let me consider the same, a classical function of p and q, which is of the same form as the quantum operator. And there are various details to this, but I take it that Douglas Smith explained this, and so I should just move on. Is that correct? Or should I go through more details? Anybody remember from Douglas Smith's lecture? What's that? Details would help. Okay, I will go through some brief details then. In that case, let me put a little hat on this h to distinguish it, this quantum operator, from that function, very briefly. The details go like this. The reason n large is good is because for large n, I can expand the exponential in a power series. This is approximately 1 minus beta h hat over n. Okay? And then I can just take the expectation, or the matrix element here. So I'll put a q and a p, and I'll put here a q and a p. Okay? And now let's again think about what this is. This h hat is again just some operator which has the form, well, let's suppose for simplicity that h hat is p hat squared plus v of q. Okay? Then I can evaluate this by, well, let's see. If I put the matrix element of 1 between q and p is clear. That's just q with p. So then I have minus beta over n. And then I want to evaluate the matrix element of q, let's see, of h hat between q and p. And you see if I stick, well, actually, let me do it this way. I've just said that h hat has this form. So let me put in p hat squared p plus v of q hat, oops, almost out of room, p. And I guess I need a parenthesis over here. So, but now this is straightforward because this is an eigenstate of the operator p hat. So this becomes simply p squared. On the other hand, this is an eigenstate of the operator q. So this becomes simply v of this q. Right? And so if I go through all of this, and we just have a place to write this, then I can, this is approximately, I can put it back up into the exponential, minus b, beta, times the Hamiltonian, the classical Hamiltonian function evaluated at the coordinate q and the momentum p. But of course, I have this phase factor left of the overlap of q with p. Okay, is that clear? Okay. Now, in cases where p and q appear multiplied together in the Hamiltonian, it's somewhat more subtle. But you see, what you do is you just commute all the q's to the left and all the p's to the right, and you get a useful answer. Okay. All right. So good. Oh, yes. So now I need to insert this into my integral. All right. You've all copied this by now. Or you can copy it later. So what I find is that the partition function is then, oh, I should mention one more thing, which of course is that in quantum mechanics, I hope you're all familiar with what this matrix element is. It is up to factors of 2 pi that I'm not going to keep track of, simply e to the I q p, right? This is the position space representation of the momentum of the wave function for a momentum eigenstate. So it's the exponential of e to the I px, or in this notation, e to the I pq or qp. Yes? Okay. If that's not familiar to you, ask one of your new friends to explain it. All right. So what then is this partition function? If I simply plug that expression in to the upper line, that is, I put this in here, I still have all these integrals, dq1, dqn, dp1, dpn, and let's see. I still have lots of factors. I still have a product from j equals 1 to n of some stuff. But the stuff is now fairly simple because the first bit has become merely e to the minus beta h of pq, pj, qj. Is that right? Yes. The bit here surrounding the exponential involves qj and pj. So that's what goes in there. And then there's another bit, which is the phase factor, which is, well, there's two bits to it, actually. There's this phase factor here that comes with this term, which involves qj and pj. So let me write that down. And you'll tell me if I've got the sign right. I, P, J, Q, J. It's the same sign I wrote over here? Yes, it is the same sign I wrote over here. Good. So we'll assume that's correct. If not, you can complex conjugate everything. Excuse me?
When you pull out the operator,
yes.
For the line to the Dutch, if you want to end in the last line is not here.
Which last one? This one here?
Yeah.
Oh, yes. Thank you very much. Indeed. This is 1 over n because it was 1 over, it's from here. Yes. Very good. Okay. So that takes care of this term here. But notice that there's another factor which involves just the phase for pj and qj minus 1. And it's the other way around. In that factor, the p is on the left and the q is on the right. So it's complex conjugated. It has the opposite sign. So this is minus qj minus 1. Okay. And again, I assume this looks somewhat familiar from Douglas Smith's lecture. What's that? Yes, you are correct. Beta over n. Very good. All right. So again, what we wish to do is take a limit as n goes to infinity. And as n becomes very large, of course, beta over n becomes very small. However, well, here I have a product of exponentials, so I could also write that as the exponential of a sum. And I'm getting more and more terms in the sum, but each term is getting smaller. In other words, each of these this whole product here is becoming the exponential of an integral over beta from 0 to beta of what is effectively p times the derivative with respect to beta of q. This is the derivative, let's see. Well, let me write this down and then it will be clear. I wish to put an I out in front, and I wish to put plus IH. Okay, now let's just check that we understand this. The idea is that in the previous line, d beta was beta over n. Okay? At a finite step in our approximation, we've approximated this differential by 1 over n of the total interval. Okay? So what I've done is, you see, here's the d beta, the beta over n. I've simply pulled that out and put it in separately. Here's the h. It's still there. The minus sign has been factored into I times I, but that's the same thing. Or conversely, up here I have the difference between two values of q at different betas. But the finite change in q is, of course, the same as the derivative of q times the change in beta, or at least is equivalent in the large n limit. So this term is simply this term, and indeed, there is the required I. Yes? Okay. And we have all of this stuff up here, which in the limit of large n, I will write in the same way that I believe Douglas did and that Tony Z did, which is that the integral over all paths q and p as functions of beta. Okay. So, we're doing path integrals again. Okay. Oh, one more comment. This is actually a cheat here. Beta does run, of course, in a sense from 0 to beta. That's how much, because that's the full amount we want here. We have n terms, each with beta over n. But recall our observation over here that the q's are arranged not in a line, so beta doesn't just run from 1 to n, but in fact they're arranged in a circle. So that beta runs from 0 to beta, but that goes back to the start. So here what we really mean, more specifically, is to integrate over a circle of length, large chalk, length beta. And by the length of the circle, what I mean is here's the circle. If I start here and measure all the way around, that's beta. Okay, that's what we're really doing. All right. Good. Okay. Questions? Yes?
Such that what you get is not topologically equivalent to a circle. You could break up that makes a difference.
I wouldn't know how to do that because I need the leftmost bra vector and the rightmost ket vector to be for the same coordinate value. Like I said, I wouldn't know how to do that because the construction that I've done necessarily links one q at j, the next one at j minus 1. No.
Oh, yeah.
They're all, if you look at this very closely, you'll find it really is a circle. It must be. Yes, okay, very good. All right. Other questions? Okay. So, of course, what we want to do here is now the same thing that Douglas Smith did. We wish to do the p integral by stationary phase methods. Okay. So since he reviewed that for you as well, we'll simply run through it. Oh, yes. Okay. So what I will in fact do, just for notation's sake, no, that's all right. We can do it directly. So if I'm going to integrate over p, when is this thing stationary? Well, it's when the variation of this action-like quantity with respect to p vanishes. So let's look at the variation of that action, the variation of the integral from 0 to beta d beta. This is a beta. P d beta q plus ih. Okay, if this is going to vanish, well, let's see. The Euler-Lagrange equations are given by just taking the derivative of the Lagrangian with respect to p. So 0 is the derivative of, let's just call it roughly L for the moment. Okay. Taking the derivative of this term with respect to p gives d beta q. Taking the derivative of this term gives plus I d h d p. Okay, good. So that So that as a result, the equation of motion here that we need to solve is d beta q equals minus I dh dp. Okay. Now, what I want to do is for a moment is to observe, or is to let's compare this with the real equation of motion for this system. The usual Euler-Lagrange equation would be dt q is equal to dh dp. Right. Okay. So this is different. And how is it related? Well, you see, let me make this more explicit. This is dq dt. This is dq d beta. So you see that they are indeed, again, related by, let's see, setting beta equals I t. Is that right? Or did I get the sign wrong? Beta equals minus I t. T equals I beta. So that if I divide this equation by I get a minus I. So is this the same thing I just tried to write down before? Beta is IT. What's that? Oh, good. Excellent. All right. Yes, T should be I beta. All right, good. So all is consistent. All right. So although this looks a bit strange, you see it's something that we should have expected. It's just saying that what we have to do is solve the equations as if the object were moving in imaginary time. Okay. And that doesn't have to mean anything physically. It's merely a formal mathematical trick, if you like, at least for the moment, which allows us to calculate the thermal properties of the system. Or what's the same in field theory, as opposed to particle mechanics, is that we solve the equations for a field living on this Euclidean spacetime. And this is why, in the end, these techniques are called Euclidean path integrals, or Euclidean field theory techniques for evaluating thermal partition functions. All right. So if one does that, if one solves these equations, and just as in Douglas Smith's lecture, we don't have to actually do it explicitly, we just simply imagine that we solve these for the momenta and substitute into the original expression, okay, what we'll end up with is then something, let's see. How should I write this? Well, okay. The thing which appears in this exponential is, as you can see, I'll put it over here. Good. The thing which appears in that exponential is p d beta q plus I h. And what we wish to do is evaluate this now, where p is some function of q and the velocity d beta q given by solving this equation here. We will define the result to be something we call minus the Euclidean Lagrangian. Just as in usual physics, we have a very similar expression without an I and with a minus sign that it relates this to the usual Lagrangian. Okay. In that case, at the very end, we can express the partition function as the integral over the remaining coordinates of e to the minus the Euclidean action, where, of course, Euclidean action is the integral d beta over that circle of the Euclidean Lagrangian. Okay. And I will mention that this sign is, in a certain sense, a convention. We simply introduce as a definition. But it has the wonderful property that if you check this for your favorite systems, the Euclidean Lagrangian is both real and positive. Okay. Okay. Good. And it is related to the Lorentzian Lagrangian by, again, replacing a t with a minus I beta. Okay. I suppose that I should make that an additional exercise to check this for some simple case, perhaps where the Hamiltonian is a harmonic oscillator, p squared plus q squared. Okay. Basically, you need a positive definite kinetic term. You need a positive definite quadratic form for momentum. Yes. No, a standard form with a positive definite function of p plus any function of q will yield a real Euclidean metric. And if the function of q is positive, then this will also be positive. If the function of q is unbounded below, then this will take both sides. Okay. But under these nice cases, where this is a positive function, the result is positive, you see this integral now, this one here, now appears to converge nicely. Because this is an exponentially damped integral. So even though there are lots of integrals to do, one can study it carefully. And I'll mention as a side that this is the way that one puts quantum field theory on a computer and studies it in lattice gauge theory. One writes down this Euclidean partition function that one can do, and that converges nicely on a computer, and one tries to extract various properties from it. Okay. So what we see from this is that one can calculate thermal properties from Euclidean things attained by analytic continuation of t to I beta. That's what we're going to do for the black hole. But first I should all right. That's right. In fact, let me just say now what we're doing in general relativity. In general relativity, of course, it's tricky because time is not a simple thing. The shape of the space is dynamical and so forth. Okay? But nevertheless, it turns out that what we want to do in general relativity, or in Euclidean gravity, thermal gravity, is exactly the same thing, but now for gravity, we replace the integral over all coordinates with an integral over all metrics. And what this means, for those of you who don't know, is we integrate over all possible shapes the space-time can take. Okay? Except that we actually don't want all possible shapes because, remember, our thermal construction involved this time circle in a very important way. Okay? So we integrate over all metrics, or all space-times, which contain a circle. Oh, and of course, this is all Euclidean metrics as opposed to Lorentzian metrics. Okay. We want all those that contain a circle of length beta. And the way this works in general relativity is typically the middle of the space can fluctuate a whole lot and gets very deformed by the matter and so forth. But if you're far away from all the matter, it does something nice. So we want this circle of length beta to not necessarily be present throughout the entire space-time, but at least, if you like, we'll say far away from all, from all matter, from all things. Okay. For those of you who would like a more technical statement, the statement is that we integrate over all asymptotically flat metrics, which are asymptotically Euclidean and, in fact, asymptotically isometric to the one we started with, d beta squared. So as we move to infinity, the metric should take the form d beta squared plus dx squared plus dy squared plus dz squared, where once again, this is a circle of length beta. Okay. So, if we could do this integral, we could calculate the thermal properties the properties of gravity in general at some temperature. But, as I believe Douglas Smith pointed out, yes, I probably do have time to finish most of my lecture, so we're getting to the good part. Once one gets this far, the rest of the calculation goes very quickly. As Douglas Smith, I'm sure, pointed out, doing this integral explicitly is typically hard, especially when the action is complicated as it is for gravity and so forth, which we haven't even given explicitly. However, one can typically, I should write this someplace else again. Let me put it here now. Oops. One can always, when it has an exponential form, try to calculate the action using stationary phase methods. So we're going to try to calculate with, again, stationary phase, meaning we want to find some space-time for which the variation of the Euclidean metric, or the Euclidean action, vanishes. Right? That's the stationary phase approximation. Okay. In other words, what we need to do to begin to calculate this thing is to simply find some, or any solution to the Euclidean equations of motion. EOM for me is equations of motion. All right. Now, here is a subtle question. Since I have not written down for you any of the Einstein equations, nor has any other lecturer in this talk, and we have not written down the Euclidean equations of motion, how could we possibly find a solution to them? The answer is we know that they're related to the regular equations of motion by this transformation. So if we happen to know any solution to the usual or Lorentzian equations of motion, if we simply replace t with I beta, we should get a solution to the Euclidean equations of motion. Yes? Plausibly. There are mathematical subtleties one might wish to check later, but plausibly, yes? Okay, good. So let me remind you of my favorite solution to the Lorentzian equations of motion. My favorite solution is the Schwarzschild solution, which we have cleverly written in two ways. One is we wrote it as ds squared is equal to minus, this is the standard form, 1 minus 2 over m over r, dt squared plus dr squared, 1 minus 2m over r, plus r squared times a two-dimensional sphere. Okay. So if I'm simply going to replace t by, is it I beta? Or, it doesn't matter, I guess. I beta. What I find is a Euclidean metric, which is, well, let's see. I get an I squared here, which cancels that minus sign. So I get 1 minus 2m over r d beta squared plus dr squared over 1 minus 2m over r plus r squared d omega 2. Well, that wasn't so hard. Okay. Yes? Yes, it is. Thank you very much. Most definitely. E meaning that I now have a Euclidean solution again. Okay. All right. There's a solution. Now, is it an interesting one? In particular, the prime question is, does it have in it this circle we're looking for? When I get far away, when r is large, does it have this circle in the beta direction? Well, it turns out that to understand the answer to that question, it helps to look down at what used to be the horizon. After all, once again, this metric is doing something funny when r equals 2m, and we should check it out. So what happens at r equals 2m? Okay? Luckily for us, we studied this region of the metric very closely last week. And we learned that near r equals 2m, we could rewrite this in a somewhat simpler form. We learned that we could write it in the form, and here I'll use the Lorentzian one first. We learned we could write it in a form related to the accelerated observers in flat spacetime. That form was minus, we called it c squared, d theta squared, plus d c squared, plus again r squared, which is a function of c, d omega 2, plus higher order terms. Okay? And in particular, this theta is nothing other than t over 4m. So now, if I replace t by I beta, it's clear that I replace theta by something else, which I will call I times theta Euclidean, where theta Euclidean is simply beta over 4m. Just working out the algebra, right? If theta is a function of t, and t is replaced by I beta, then theta also becomes imaginary, and we can get rid of the I by simply labeling it as I times some Euclidean angle. Here's the answer. Okay? So what do we have then from this one? Well, in that case, near r equals 2m, the Euclidean metric becomes plus c squared, because the I square is here, to cancel that, d theta Euclidean squared, plus dc squared, plus r squared c, d omega 2, plus higher terms. Okay. Now, here's a question for the more advanced students. Okay. For those of you who are not yet so advanced, you will check this. I've given as an exercise to check the following statement. But for the more advanced students, do you recognize this metric? Those of you who've had a little bit of general relativity. Yes? Oh, I'm sorry. I have been using this notation. Thank you. For consistency, very good. Okay. Does anyone recognize this metric? Yes. This is, in fact, the metric of flat Euclidean space but written in polar coordinates. In other words, you can verify for yourself as an exercise that this term that I have selected out here is the same as dx squared plus dy squared, just that thing that gave us the Pythagorean theorem, okay, where we have related x equals c cosine theta Euclidean and y equals c sine theta Euclidean. I'll let you do the math to check that out. So what we find is that we were perhaps worried that near r equals 2m, this this solution would behave badly, because there's at r equals 2m, that term goes to 0, and this one diverges. Okay? But we find that that's not necessarily so. We find that, in fact, at least when treated properly, near the horizon, the space-time becomes just like that of a flat Euclidean plane. Okay? Now, what's the one subtlety? What part do we have to treat properly? Well, if theta e is the angle of polar coordinates, does it live on a line or does it live on a circle? It lives on a circle, right? And over what values is it allowed to range? Well, it's got to be in 0 to 2 pi. Okay? So what we find is that this clever trick gives us a nice Euclidean solution so long as this angle lives on a circle from 0 to 2 pi. So therefore, since beta is theta e over times 4m, we see that beta lives on a circle which runs from 0 to 8 pi m. Okay. So the black hole, to finish this up quickly, I can say a few more words about it at the beginning of my next story. This is the main point. The black hole is related to a thermal field theory calculation so long as this parameter beta is chosen to go from 0 to 8 pi m. And therefore, you will recall that the temperature is 1 over beta. So the temperature of a black hole is 1 over 8 pi m. And this is exactly the result that Stephen Hawking found via a somewhat longer and more complicated calculation, which is reviewed for you in those lectures, in particular by Ted Jacobson, that I referenced at the beginning. Okay, so I'm essentially out of time, so let me pause here and see if there are a few questions.
Questions?
Yes? Okay, all right, so I have realized after the talk that I use a slightly confusing notation. You see, it's visible here. I have used beta as both the integration variable and the limit of integration, okay, which one often does but can be confusing in just this way. So here, I mean the coordinate on the space-time, which is in the integration variable in the action. Here, what I really mean is the upper limit of beta, the total value through which it goes. Okay, good question. No more questions. All right. Well, I have been asked to give another discussion, some more lectures and so forth, or partial lecture and so forth. So if you think of more questions over the next few days, please either ask me directly or let me know so that I can know what to talk about on Friday. And I'm happy to say a few more words about this, although I've finished the basic story here, or I can tell you about other things with black holes. Great. All right.